This is a lecture, a continuing lecture in a series covering first order systems. This is part 6, and in this lecture we're going to just work one problem, and it's a little more complicated problem, and one that involves a switch in the circuit, and that switch will actually switch positions at time 0, and so part of the problem will actually be finding the initial conditions to apply for our inductor or capacitor. So here's the circuit. I'm going to draw, it's kind of drawn, it's a little convoluted in how it is drawn, purposefully I should say. I should add 90 ohms here. We have this switch, okay, that connects an 18 volt source to the circuit, and it is initially closed. What will happen is the switch will open at time equal to 0. That's what makes this problem interesting. We have a 1 millihenry inductor, and then we have a 2 millihenry inductor, and then we have a 3 millihenry inductor. Okay, and we have this current we call IL here. And we're going to call the current going down through the 90 ohms I1. Okay, and the question is, find I1 of t for t less than 0 and for t greater than 0. That is our task. So, what we need to do is, we're not told what the initial condition on the current is, but we are told that the switch is closed, and we can assume that the switch has been closed from time infinity past, and it will open up at time 0. So let's draw the circuit. So let's redraw circuit for t less than 0. Okay. So what we have is we have our 18 volt source. It's connected to 90 ohms. I'll make sure we label our I1 here. And in parallel with that is the branch consisting of the 60 plus 120 ohms. So I'm going to go ahead and write 120 plus 60, which is equal to 180 ohms. And then we have, in series with that, we have an inductor, which I'm going to draw one inductor at this point, and we're going to replace these inductors with equivalent inductance. Okay, now it turns out when you combine inductors in series or in parallel, they combine like resistors. Okay, so the equivalent inductance, LEQ, okay, is going to be equal to 1 millihenry plus the parallel combination of the 2 millihenry and the 3 millihenry. So this will be equal to 1 plus 6 over 4 millihenry, which will be equal to 10 fourths. 10 fourths of a millihenry, or in other words, LEQ is equal to 2.5 millihenry. Okay, 2.5 millihenry. So that is a somewhat simplified circuit. Okay, so notice that let me pause this. Okay, I paused it because I just realized I left something out of this circuit that's pretty important. I left a resistor out of it. There's one more resistor here. It is a 50 ohm resistor. Okay, 60 ohm is this guy here. I left out the 50 ohm resistor. So let me put that in right here. We have 50 ohms. Now we can redraw this as 18 volts. The 90 ohms and the 180 I can write over here. I can draw over to this side. I can say this is 180, this is 90, and here is I1. Okay, and then I have 50 ohms, and I have my inductor LEQ, which is 2.5 millihenry. So what is the initial condition of IL? So this is the circuit for time less than 0. So from infinity past we've had this circuit. Notice that the 90 ohms and the 180 ohms are hanging in parallel with the 18 volts, and therefore they have no bearing at all on the current that is actually going to flow through IL. The current IL is going to be equal, very simply, to just the 18 volts divided by the 50 ohms. Okay, this is because we assume that after infinite time, in other words, from minus infinite time to 0 time, okay, the circuit is in steady state. It's in steady state, meaning dIL dt is equal to 0, right? And if that's the case, V equals L di dt, that means VL is equal to 0. So if VL is equal to 0, then all of the 18 volts is placed across the 50 ohms. None of it is placed across the inductor. In fact, what you do when you're looking at a steady state condition like this, where the system is driven by a DC source, you actually will short the inductor, right? We short the inductor. That's essentially what we're saying here, is because VL is equal to 0, the inductor really appears like a short when everything is static and not changing in time. So the 18 volts goes across the 50 ohms. So from this we can say that IL at T0 minus, in other words, just before the switch opens, is going to be equal to 18 over 50, or that's approximately 0.36 amps. This is actually valid for all time less than 0. Okay, that becomes our initial condition. Again, I put the 0 minus there, just meaning like a smidgen of time before time 0, because we've said at time 0 the switch is opening. Okay, now we can also consider I1 for, at time 0 minus. Okay, what kind of current do we have flowing there? Well, in that case, I1 at time 0 minus is nothing more than just 18 volts over the 90 ohms. Again, the 90 ohms is straight across the 18 volts. Nothing else has any bearing on the current I1 except for the 90 ohms. So it's 18 volts divided by 90 ohms, which is 0.2 amps. So all the work that we've done so far has been just to determine what is the initial condition on the inductor current. And we're now ready to actually solve the time domain response of the inductor current, and we'll make use of the initial condition to find the complete response. So at time 0 the switch opens, and now there is no voltage source. Okay, so let's redraw circuit for t greater than 0. Okay, in other words, switch is open, and up here it was for switch is closed. So when the switch is opened, what we have is we have the 90 ohms to ground. We have the 120 plus 60 ohms, or 180 ohms, to ground. We have 50 ohms, and then we have our L EQ. Right, and we have IL flowing this way. Okay. Now, the equivalent resistance that we see, that the inductor sees, is going to be REQ equal to 50 plus 90 in parallel with 180, which is equal to 50 plus 110 ohms. So REQ is 160 ohms. Okay, so from this we can write that therefore tau is equal to L over R will be equal to, let's see, 2.5 millihenry divided by 160 ohms. So tau will be equal to, let's see, let me do some math here. No, I'm sorry, I did that wrong. The 90 in parallel with 180 is equal to 60. 60. And so the total here, 50 plus 60, is 110. Okay. So it's 2.5 millihenry over 110. Oh boy, I made all kind of mistakes now. Okay, now I realize that this is a mistake up here. When I did the parallel combination of the 2 millihenry and the 3, that's 2 times 3 over 2 plus 3. So that's 6/5. 6/5 of a millihenry. So we don't have, we end up with 11/5. 11/5 of a millihenry. Okay. Where else did that go? So this is, let me just cross this out, tau is equal to 11/5 of a millihenry divided by 110 ohms, and that should equal 20 microseconds. Okay, so now we can write that, we can take all this and say, therefore, okay, the current for time t greater than 0, IL, and we can actually say greater than or equal to 0 because IL can't change in 0 time. So IL of t is going to be equal to its initial condition, okay, the current at what we found to be IL at time 0 minus, and incidentally this is equal to IL of 0 because current in an inductor cannot change in 0 time. This will be times e to the t over tau, where tau is going to be 20 microseconds. Okay, so the inductor current is going to just decay, and it will start out at the initial value of, what did we say, 0.36 amps. Okay, 0.36 amps is IL. Okay, now the last thing we need to do is to find what I1 is. Okay, well, I1 is going to be a current division version of IL, right? Find I1. Okay, current division of IL. So we'll have, I1 is equal to, notice the direction, IL is pointing the opposite direction as I1, so it's going to be a minus IL. And that current is going to split between the 90 and the 180. So it will be 180 over 180 plus 90. So minus 18 over 27 times IL, which IL is equal to IL times 0, e to the minus t over tau. This all evaluates to, let's see, it will be minus 0.24 amps times e to the minus t over tau. So this ends up looking like this here, where it starts at minus 0.24. So now let's put all this together. We'll plot both IL and I1. Okay, prior to time 0, we had the current up here at 0.36 amps, and we had the current going through I1 down at 0.2 amps. Okay, so this is IL, this is I1. Okay. After time t0, when the switch opens, we now get the inductor current is exponentially decaying down to 0. Okay. That is described right here. Right? So that describes this. But I1 is described by this expression here. And so you have this discontinuity that the current jumps from being at 0.2 amps to going down to minus 0.24 amps. And now it's going to exponentially decay back up to 0. Okay, so I1 looks like this. This might be very surprising to you. Okay, and we'll go back to the circuit and see if we can understand why. So initially, where I'm looking at the initial circuit here, or actually I could look at, let's say here, so we have the switch here. I'm going to look at this circuit right up here. We have the switch, all right, and the switch is going to eventually open at t equal to 0. So prior to time t0, there is 18 volts divided by 90 ohms flowing through the 90 ohm resistor. So I1 is positive. And the I1 being positive is due purely to the 18 volts being across the 90 ohms. But at the same time, while the switch is closed, there is current being supplied from the 18 volts over to the inductor, producing a current, a clockwise current IL. Now when you open the circuit, the switch, there now is no longer any current flowing from the 18 volts down through I1. The only current that remains is current that is flowing through the inductor in a clockwise direction to the right of I1. And so now you have a net contribution to I1, which is a negative current, and it's due completely to this positive IL that is circulating clockwise and coming back up through the 90 ohms. Now, not all of the IL current flows through the 90 ohms because we have 90 ohms in parallel with the 180 ohms, so you get some current division there. So this is a typical problem that you would see that involves finding the initial conditions of a circuit that has an inductor or capacitor, and then actually using that initial condition to solve for the complete solution for the circuit. Now notice in this case, when we say complete solution, it turned out that once the switch opened, there was no voltage or current source driving the system. The only thing that was left was the equivalent inductance and some equivalent resistance. So it was purely a homogeneous response, if you will. And that's reflected by this equation right here, where I'll say homogeneous, okay, because there's no source. There's no source driving this. We're just watching the inductor current extinguish itself as it flows through resistors and gives up energy to those resistors.